Okay, hi everybody. We're welcome back to my YouTube channel. Hopefully we're all. Hopefully, for the record, this is annoying. So section 6.7 is investigating graphs of polynomial functions. What do we know based on graphs? Like, and how? What can we tell about a polynomial, or the graph of a polynomial, just by looking at the equation? Like, thinking back to the beginning of the year, I said to you guys, for every function that we will learn, you will be able to look at the equation and know exactly what it's doing without actually having to go into your graphing calculator and plugging it in. So that's what we're going to do today. I'm going to give you a polynomial, and you're going to be able to visualize exactly what's going on. Now, to do that, let's start by looking at some patterns. Okay, let's start by looking at some patterns. At the beginning of the year, and you don't need to have this chart in your notes. This is not anything you need to write down or anything. At the beginning of the year, we looked at a bunch of different parent functions. Okay, these are the polynomial parent functions. We also looked at square roots and absolute value and whatnot, but these are the polynomial ones. I want to start today by asking you to find patterns, because that's what math is, right? All of math is just finding patterns to fit different situations and creating rules off those patterns. So what's one pattern that you can see off of those graphs? What do you think?
The one that has is the group degree of 2, it has a 1 like curve and so on and so forth, and the first one is an n. So. Okay,
so that's a good point that she brings up, and this is one of the observations that we need to make here. She said that the quadratic, the degree of 2, has one, we're going to call those turning points. It has one turning point. How many did the degree of 1 have? None. So the degree of 2 has 1. How many does the degree of 3? Then 4. So the rule that we can make off of that, and this is one of the observations that we wanted to make here, the rule about turning points. Okay, the rule about turning points, or you could call them changes in direction. How does that associate to the degree number? It's 1 less. If n is the degree, the function will have n minus 1 turning points. Okay, that's one of the observations that we're going to make. And that we will get to the notes about that on the second to last slide, way down here. Okay, what other observations can we make? What else do we see? Al?
Degree 4 looks like a W.
That's true. Very good. Degree 4 looks like a W. Yes. W.
Did you not say W? It's like double line. There's 2 U's.
You always been saying it like that.
No, W.
Oh, okay.
W.
So there's an announcement on the board.
I'll use that after we turn off.
I understand. At the end of the video.
Yeah, what else do we see?
Black line.
Thank you, Burkett. Yeah, for the record, Burkett said the axes of the coordinate plane are perpendicular. Yeah, excuse me. He said it a little bit more. How do I put this?
I was
Intellectually inferior. The black lines are. At least you didn't say like the black lines are crossy ways.
They are.
Okay, what other patterns do we see? Yes, that's right. Thank you.
It crosses the x-axis the same amount of degrees.
Okay, good. And what is that? Does anyone remember what that's called? The fundamental theorem of algebra. Right? That is the fundamental theorem of algebra that says that the degrees matches the number of zeros it will have. Now, that includes any multiplicities. Okay, done talking now. Thank you. The degree matches the number of zeros, including multiplicities, and all of these, with the exception of degree 2, look like they're going straight through, right? It looks like the quadratic has a bouncing off point, which isn't even root, so it would have 2 there. The degree matches the number of roots. That's the fundamental theorem of algebra. Good. What other patterns do we notice? There's one more key one that we need to see before we move on. Dominic.
For even powers, they all like when you're done, they all kind of go back up the same way, but for odd, they go the opposite way.
Very good. That is called end behavior, right? That is called end behavior. The end behavior for even degrees, the end behavior is the same. They will both go up, or they may both go down. For odd degrees, it's one of each. Okay, we don't know yet whether it goes down on the left, or up on the right, or up on the left, or down on the right. But for right now, we can say the end behavior is the same for even degrees. The end behavior is different for odd degrees. Okay, good. We've gotten to three main things that I wanted us to see: the roots, the turning points, and the end behavior. Let's start by discussing the end behavior. Okay. Now, when we talk about end behavior, like Dominic put it really well, but it's hard to talk about. It's like, okay, when you're done graphing it on the right side, it's going to go up, and when you're done when you start on the left side, it's going to go up too. How do you really use mathematical language to talk about things like that? Well, we have this terminology where we say x approaches positive infinity and x approaches negative infinity. You don't have to write this down just yet. Trust me, I'll write it down in a second. We have this idea of having x arrow. That arrow in math language means it approaches that value. So as x gets closer and closer and closer to positive infinity, meaning, well, where do my x's go when they get more positive and more positive? They go to the right, right? Where do my x's go as they get more and more negative? They go to the left. So what we're going to do is make statements by saying, as x approaches positive infinity, which basically means on the right side, it's going to do something. And as x approaches negative infinity, it's going to be more negative. It's on the left side, it's going to do something. Yes. Where are you going next? Well,
Rip Archie. Recipes.
Okay. So we have this idea of being able to talk about on the right side and on the left side. But we still have not had the rules about, well, what happens on the right side, what happens on the left side, and what causes those things to happen. Well, actually, the leading coefficients and the degree determine the end behavior. It's funny that, I've been teaching my Algebra 1 students how to identify what a leading coefficient is when putting it in standard form, and how to identify the degree of a polynomial. They can identify it, but they have no idea what that means just quite yet, right? It's not until this point until you learn, okay, exactly what the degree actually means, that it has so many different relationships to turning points and zeros and end behavior and what it's going to look like on the graph. So I'm going to give you a table here, and this is the part where you're going to need to write down. That's the top half of the table. I didn't want to show you the entire thing right now because I'd have to zoom it out and you would never be able to see it. Definitely write down this table. Now, I'm going to make an edit to the left side. On the left side, we're talking about the leading coefficient. On the top, in the columns, we're talking about the degrees. The rows are the leading coefficients. What's another way to say the leading coefficient is greater than 0? That it's positive, right? So we're going to say the LC is positive. Down here, we're going to say the leading coefficient is negative. All right, I'll give you a minute to write that down. Again, this is the top half of the table. You have to learn the notation. You have to learn how to talk about it. You have to learn the language a little bit to be able to answer these questions. Because I'm going to ask you, okay, if it's a positive even, what's the end behavior? And you have to use this terminology. So again, the two parameters that we're looking at are what is the degree, and I don't really care about the numeric value of the degree. I only care about whether it's odd or even. Okay? I only care about whether it's odd or even. And then I look at the leading coefficient. And again, I don't care what the number is. I don't care what the number is. I only care about whether it's positive or negative. I don't care what the number is. I only care about whether it's positive or negative. It could be a 6, but I don't care that it's a 6. I care that it's a positive 6. Positive. The degree could be quintic, a 5. But I don't care that it's a 5. I care that it's odd. Okay, so I'm going to start describing what you see there in each box. Okay, so positive, odd. Positive, odd. This is if we have a positive leading coefficient and an odd degree. Now, the notation is saying, as x approaches positive infinity, comma, p of x, the function, also approaches positive infinity. Now, what does that mean? What does that mean in English? Okay, as x gets bigger and bigger and bigger, right? As x approaches positive infinity. Is that right side or left side in behavior? As x approaches more positive and more positive and more positive. That's right side, right? So on the right, now the function p of x approaches positive infinity. Now, isn't p of x just another fancy way to say y? The y values also go up. It increases. So they go up. On the right, it goes up. On the flip side of that, this would be on the left. As x approaches negative infinity, as x keeps getting smaller and smaller and smaller and smaller, that would be on the left. The function will go down. P of x will approach negative infinity. The y values will decrease and decrease and decrease, meaning it will go down. So that's up on the right, down on the left. That's positive, odd. Positive, even, both going the same direction. Now, I don't know why they put like the right side end behavior on top and the left side down below. And then they put the left side on top. I don't know. This is on the left side. It will go up. On the right side, it will also go up. Now, when I ask you for the end behavior, you can't just tell me like right, up, left, up. No, I need this formal notation. As x approaches positive infinity, blah. As x approaches negative infinity. Right? You have to finish that sentence. Because what you're saying there is you're saying, okay, on the left side, as x approaches negative infinity, then you finish your sentence. What is it doing? Is it going up or down? If it's going up, p of x approaches positive infinity. If it's going down, p of x approaches negative infinity. Okay, you can see where this is going. Down below, the leading coefficient is going to be negative. The LC is going to be negative. Does anybody still need the top half of the chart? Perfect. Is that the box?
Yeah.
Okay, so as x approaches negative infinity, so again, they're saying on the left side up top there, on the left, p of x goes up, positive infinity. As x approaches positive infinity, on the right side, p of x goes down. For negative even, on the left side, it goes down, and it will also go down on the right side. So this is end behavior. This is how we describe end behavior. As x approaches positive infinity, it's going to go up or down. As x approaches negative infinity, it's going to go up or down. We have 4 different options to do. Remember that, like, when you're doing these problems, you can start, like, as soon as I ask you, tell me the end behavior, I mean, you can start by doing this. As x approaches positive infinity, well, that's a bad infinity sentence. And make a comma, because you're going to finish that sentence, and then you're going to make a new sentence as x approaches negative infinity. I don't care whether you do the left side or the right side first, it doesn't matter. But basically, you're just going to fill in these blanks with what it's doing on the right and left side. Now, you have to memorize what it's doing on the right and left side. Remember that there's only 4 options, though. And I'm going to teach you a little fun way to remember it. Dominic.
Instead of saying p of x approaches, could you say y approaches?
Yeah, that's fine. You know, I'm going to give you the name of the function, so you're just going to use the name of the function. Yeah, but that's right. You're technically just saying the y values are doing something. Yeah. Winter formal's coming up in a few weeks, right? Right. So I'm going to teach you guys a little dance. Everybody stretch out. You don't want to pull them off. Come on now. Stretch your arms out.
Are you available?
Ryan, are you stretching right
Am I
now?
available?
Why
Why, you going to ask me to go? That's weird. Okay.
Ryan, you're supposed to be stretching.
Although my shoulder is really tight because I had to hold my 9-month-old from 2 in the morning to 4 in the morning last night. She just decided to be up. She was just like awake.
Dude,
Right eye,
I had to
like,
hold I hate when that happens.
Oh my God.
I thought you was still.
All right, so here's what we got. Okay. Now we know that if it's even, it's going to go in the same direction, right? They're either both going to up or both going to go up or both going to go down, right? And when they're odd, it's going to be one of each. Okay, so here we go. Everybody do this with me. Okay, first one is positive even.
Ryan, you're not.
Negative even.
Negative even.
Positive odd.
Positive.
Negative odd.
Negative.
There you go. And that is the end behavior dance.
Wow.
Dude, that is kind of nice.
Positive even.
Positive even.
Negative even.
Negative.
Positive odd. Negative odd. Now you got to know the choreography. You better put your right arm up first when you're doing this, because if you go positive, negative, positive, that's not positive. Positive, negative, positive, negative. Yeah? It's called the end behavior dance. So when you're out on the dance floor, winter formal, and you're like, you know, like some groove music comes on. All right, let's test it out. Let's test this out. Okay. Because you know, I mean, if you start doing that dance, like somebody's gonna be like, oh,
Yeah.
look at that guy. In the best way possible, not in a bad way.
Oh gosh, I should ask.
All right. Okay. Max, what is my leading coefficient?
-1.
-1. My LC is don't clap for that. Is -1. Do I care about the fact that it's 1?
Yes.
No, I care about the fact that it is negative. Now, my degree is what? 4. Do I care about the numeric value? No, I only care about that it's even. Okay, so here we go. Negative even, right? Positive even? Negative even, there we are. Down, negative even is both down. So what I like to do is just draw myself a little diagram. I know that it's going to go down. These were my arms, right? It's going to go down on either side. So what does that mean? So if I'm writing it out formally, you know, we can always start like this. I don't know why I usually put, I don't know why I did it switched over there. I usually put my left side first. I don't know, I read right to left, so I guess maybe that's why. And then I'll put the right side. Okay, so as x approaches negative infinity, what is happening on the left side? It's going down, right? So that would mean my function, q of x goes down. On the right side, the function goes down as well. So on the right, q of x decreases as well. That's how we describe the end behavior. This says, again, in English, as x decreases, the function decreases, the y value decreases. As x increases, the function decreases, the y value decreases. Let's try that again. So we've got p of x is 2x to the fifth plus 6x to the, I don't really care. Because we're talking about just end behavior, right? So what's the important piece here? What's my leading coefficient? It's 2, which is positive. The degree is 5. It's odd. Positive odd. So here we go. Positive even, negative even, positive odd. Right arm up, left arm down. Right arm up, left arm down. Right arm up, left arm down. Right up, left down. Okay, so as x approaches negative infinity, so on the left side, it's going down. P of x goes down. On the right side, the function, oops, that's comma, P of x increases, goes up. Let's do one more. Wait. Huh? Wait. We good? What? Yeah. What? Okay, let's try this one. We got r of x. Okay, we've got a negative odd, right? A negative odd. Okay, so we say positive, negative, positive, negative. Negative odd. Negative odd. Okay, so we have on the left side, it goes up. On the right side, it goes down. Okay? Questions about that? Yeah.
Why do you keep changing the letters? Like it's like R of X.
Just to be fancy.
Okay.
No, it's that's where this came from.
Oh, I see.
He's got it now. Questions? Okay, now let's try to match what we see on the graph. So what do we see there? Positive, negative, positive, negative, odd. We know this is a negative odd function. Now, we can even go so far as to classify this. How many, well, what's my degree here? 5. Because I see 5 intersection points to the x-axis. So I know the degree has to be 5. Do I see any bouncing or bending through? I don't see any bouncing or bending through. It looks like these all go straight through. And I see 1, 2, 3, 4 changes in direction, which would mean that's a quintet. If that's a degree. Well, right now we're only concerned about positive, negative, even odd. Oh, first one, touchdown. Positive, even. Positive, positive, even. Does that make sense? Okay. All right. Let's do the fun part of today.
No way.
I mean,
Dude, which means
that was
it's
kind of
better.
but
We're doing the funner part.
the funner part. Yeah, the funner part. Thank you.
You were swear to God,
For you.
all the way over here.
This is for you. I already know how to do all of this stuff. You know, like I teach for you.
Are you
Oh,
sure?
yeah,
I teach for you. Like I already have the joy of math in my heart, and I'm just trying to share it with you, right? So that you have the same joy in your heart.
Yeah.
You know who else is the same way?
All right, here we go. So on your test and on your group test, there will be a no graphing calculator portion, and this is the bulk of the part. It's a bulk of the no calculator portion. Okay. So let's graph this function. Now we know now. What's the degree? 3. How many intersection points of the x-axis should I have?
3.
How many changes in direction should I have?
2.
What's the end behavior? Positive odd, right? Positive, negative, positive odd. Positive odd. Now, does it like formally ask for the end behavior? No. So I'm just going to make a note to myself saying, okay, on the right side it goes up, on the left side it goes down. Because that's going to inform how I graph it a little bit later. This is the only one that we're going to do like this, guys, and I think we should really write this one down.
Oh, okay.
Just saying. Now, if I can't, the next thing I have to do is figure out what my zeros are. If I can't have my graphing calculator to find my zeros, what should I do then? You're right, I would try to factor, but does this factor?
Yes.
No, it does not. It does not. So what do I have to do? The P's and Q's, good. I have to do the P's and Q's. Oh, you're fine. There's a Q value of 1, relax. So the P list is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. I said you'd have to do it on your test, and this is where you have to do it on your test. Okay, my Q value is 1, and again, P is negative 6, right? That's where I got all those factors. They're the factors of 6. The Q value is 1, so plus or minus 1. I'll tell you this, on the individual test, the Q value is 1. You're welcome. On the group test, it's not. But on the individual test, the Q value is 1. Okay, so my P over Q list is really just my P list. So I have 8 different options to choose from to find my zeros. Okay, who's a good guesser? 3? I heard a 3 out there.
The answer's negative.
I heard a 3.
It's negative 2.
Let's try a 3.
It's negative. It's negative 2.
It's negative 3.
Let's try a 3 first. Uh-oh. It's getting out of hand quickly. That's not going to work.
Try negative 2.
Let's try negative 3.
Or.
Get this out of here. Let's try negative 3. 1, negative 3, a 1, a negative 3, a negative 2.
I told you it was negative 2.
Okay, so that means that this crosses the x-axis at negative 3. The factor is x plus 3, leaving an x squared plus x minus 2. Okay, that factors though. So we've got an x plus 3, and then we've got, because if this didn't factor, I would have to go to the quadratic formula. Now this factors though, so we've got an x plus 2, x minus 1. So therefore my 3 roots are negative 3, negative 2, and positive 1. Everybody following me there? So let's graph that. Let's graph those 3 roots. Positive 1, negative 2, negative 3. Okay, remember the end behavior the end behavior is going to tell us what's happening on either side. On the far left of the leftmost x-intercept, and on the far right of my rightmost x-intercept. So what was it again? Down on the left, up on the right? Yeah. So what I can do is just go down on the left, up on the right. Now, I don't really know how steep that's happening. If I really wanted to, I could go in and plot some values. But for right now, I'm okay with you just knowing what the end behavior should be and plot it accordingly, just putting the arrows on the end of your x-intercepts. Now, what's happening in between there? How high or low do my points get? Well, let's just make a table of values. Let's strategically pick them so that we can see where it ends up. So what's a good number to pick in between -2 and -3? In between -2 and -3. Thank you. Now, what else would be a good one to pick in between -2 and 1? 0. However, look. What if what would happen if we plugged in 0? What would we get? Do we all see it here? Guys, the intercept, the y-intercept, just like it was when we were working with linear functions, is just the number sitting out there on the end. Right? Just like quadratics, it's the number sitting out there on the end. Same thing with polynomials. It's the constant sitting out there on the end. So the the y-intercept is -6. So use that point. So let's pick a different one other than -6 to figure out what's going on in between there. Maybe -1. Oh. Thanks. So let's pick it and see what happens. Let's plug it in. There we go. Smartboard magic there. I plug in -2.5, I get 0.875.
Wait, so we're allowed to use our graphing calculator for that?
You're allowed to use a calculator. I didn't need the graphing functions of my graphing.
I don't know. What's graphing calculator? Well, now I'm reading these.
Woosa. So we've got 0.875 and -1, -4. There we are. Okay. Does that make sense? What did I do wrong? What's wrong?
Not doing that.
What's your issue?
I have you.
Where did I lose you? Okay, now you have, guys, stop talking. Stop talking. You have to pick points in between each 0 to figure out how high or low it goes. Okay? That's why I made this table of values. You don't need to do that on either side. Like if I really was picky, I'd make you pick a point to the left of -3 and a point to the right of +1. But I'm not going to do that because you know in behavior. So what I would like you to do is pick a point in between here and here, and pick a point in between here and here. You can use the y-intercept because you could just pick it out of the equation, but I want you to pick another point in there so that you can run something else to see an actual curve. Like when I plugged in -1, I got -4. Where did I plug -1 into? I just plugged it into the equation. Like I did -1 to the 3rd power plus 4 times -1 squared plus -1 minus 6. And it got me -4. Okay? I just ran my values through the function and see where it ended up. Okay? Questions about that? All right, last thing that we're going to do is, it's kind of a sidestep here. We talked about that idea of turning points, right? The reason why we're sidestepping a little bit right now is because for this, you must have your graphing calculator, okay? I have to give this to you on a graphing calculator portion. What we're going to do right now is figure out what the peaks and valleys actually are. Like remember back to quadratics? If I gave you a parabola, a U-shape, I could pick out, and the vertex was a minimum value. I could actually calculate what that is using negative b over 2a and then plugging that in. You can't do that with polynomials. You can't do that. You can't find maximum and minimum values with an equation. So what you have to do is actually have to go on your calculator and find those. Like, for example, this. Let me plug this in my calculator. Done. In, right? 2x cubed minus 18x plus 1. I'm going to get it back to my standard 10 by 10 window. Do I see my high and low points on my graph right now? No. Bummer. I've got to change my window so that I see my high and low points. Because I did this earlier today, I know that my y value needs to go down to negative 30, and my y maximum value has to go up to positive 30. I'm just changing my window. I'm changing my window so that it goes down to negative 30 and up to positive 30. Now do I see my maximum and minimum values? So all I need to do now is calculate them. Well, that means I'm going to go into the calculate button. So now if I want to find a maximum point, like the one that I have on the left side, I choose maximum, and then I go somewhere to the left of my peak, somewhere to the right of the peak, and then I hit enter, and that is my maximum value. The y value is my maximum value. If I wanted to find a minimum, like this one to the right, I would just calculate the minimum value. Left boundary, somewhere to the left of the valley, somewhere to the right of the valley, and then I go somewhere in the middle. And coincidentally, or not so coincidentally, they have the same decimal. Isn't that interesting? That's kind of cool. All right, questions about that? Homework is, let me write it down. We got 1 minute. You can check on Canvas to find it too, but the homework is page 457 to 458. Whoops, that's a 458. Sorry. 15 to 22, 24, 25, 28, and 30. Okay. Those are and behavior. Those are graphing. Those are find local maximum and minimum values. I'm going to turn off the video real quick. Hold on.
Do an announcement.
So long, everybody.
Goodbye.